And we go to the second talk, which will be given by Mr. Aditya Tripathi from Australian National University. Aditya, could you share the presentation, please?
Yeah. Am I audible?
Yep.
Yeah. Is my presentation visible? Yeah.
Yeah. So, and Adi will be talking about active nanophotonics for robust chip-scale optical devices. So, Adi, please.
Thank you very much for the introduction. So, my field of research is active nanophotonics, which is definitely for device applications. My supervisors are Dr. Sergey Kruk and Professor Kivshar. So, first of all, I would like to acknowledge all the people who have collaborated with us and contributed to this research. It's Australian National University, Oak Ridge National Labs, Korea University, UTS, ITMO, Purdue, and in CNRS in France as well. So what is active nanophotonics? Active nanophotonics involves basically marriage of two concepts, active media, and which is like upconversion nanoparticles, perovskites, TMDCs, quantum wells, exchange media, with nanophotonics, which is like BICs, topology, PT symmetry, exceptional points, Anapoles, Huygens metasurfaces, or many other things as well. So basically, we try to combine these two things to make new applications, like new devices. Now, first part of my research is active media along with topological photonics. These are the people who have contributed. And first, before going to topological photonics, I must throw some light on topology. What is topology? It's basically a branch of math which deals with properties which are preserved under deformation. And these different topologies are characterized by topological invariants, which are integers. Like, okay, so cup to donut, like the number of holes is preserved. So number of holes is a kind of topological invariant, which is like, it is like a system property. It's like, it characterizes its global behavior, like bulk behavior. What are topological edge states? Let's assume we have topological material 1, like material A and material B, which have different topological invariants. Now, like if you have different topological invariants, you cannot jump from one material to another material. You have to have a topological phase transition, and this phase transition is smoothened by topological edge states. Like, and this has been realized in photonics. So in photonics in 2013, this is a very good example of two topologically distinct media, material A and material B. And you can see that at the edge, we have this propagating edge state, which is not affected by the disorder here, and which makes it a very good candidate for making optical waveguide or like you exploiting this in a device. Topological protection of Australian continent, like although it's already topologically protected, water and land are probably different, but still. So first of all, we try to use topology for protection of nanoscale light emitters. Like we have two structures, like optical analog of graphene, optical analog of polyacetylene. Both are topologically very, very interesting. First of all, I'll go through the one-dimensional structure, which is topological analog of polyacetylene. And so we had this structure called of zigzags, which was already published in 2015 and in 2019. Like and even in 2017. So the idea was to first of all study its edge states, which were electric dipole and magnetic dipole modes, and I calculated them using console, and it was found that they all lie in the region of 1530 and around that. You can see both the edge states are excited in the inset. On the right hand side figure. Theoretical calculations, they demonstrated that we have a good edge state response at around 1500 nanometers. Now, this 1500 nanometers also happens to be the wavelength, the active wavelength for rare earth doped nanoparticles, which is another active media, which our collaborator in University of Technology, Sydney, Professor Dayong Jin, specializes in. So we wanted to couple these two, like we wanted to have efficient coupling of edge states with rare doped nanoparticles to observe polarization, like to observe controlled photoluminescence from these nanoparticles. So since these nanoparticles also have photoluminescence in 1530 nanometers, so we presume that it would couple really well. So it was our samples were sent to UTS and they spin coated the samples with these nanoparticles, and we measured them here in ANU. What we found was that the photoluminescence from the samples coated with these nanoparticles was way higher, like 5 times higher than photoluminescence from nanoparticles on these on substrate, which proved that which indicated the presence of very strong coupling. And this coupling, we also analyzed the polarization from this coupling, and we found that at the edges of the topological chain, the edge there the polarization of emission from the from the rare doped nanoparticles uh, was controlled. It was the same as the edge states in simple in uncoated nanostructures, which also proved that we control the polarization of nanoparticles through our topological nanostructures, which was a pretty cool result in the first place for us to observe, because normally controlling polarization from such nanoparticles requires precise alignment of each single nanoparticle, which is very difficult to achieve from basic methods like spin coating, but with the use of topological nanostructures, by the means of coupling with topological nanostructures, we can observe that we have polarized emission without spending a lot of money on fabrication procedure. Now, this was published in Nanophotonics as topological nanophotonics photoluminescence control in 2020. And like this experiment was performed on our setup over here, which we built on this optical table. A simple setup with near infrared objective and spectrometer and 980 nanometer laser diode. So the second part of the topology section involves 2D topological nanostructures. These have been pretty extensively studied because they are optical analogs of graphene. They have Dirac cones, and we eventually exploited this property of Dirac cones to make topological photonic topological insulators. What we do here is that in the blue triangle inside we have a different topological invariant, and in the outer material we have different topological invariant, and this creates a topological edge or a topological domain wall at the sides of this triangle. And this structure has also been studied acoustically in acoustic lattices, and they inserted they introduced defects in this lattice, and still they observed that uh, the mode in this cavity in the topological domain wall fully propagates, which makes it a very good candidate to exploit for devices because it's robust to disorder. Now, we wanted to use this for lasing, and for this purpose, we created this lattice with quantum wells, and which served the purpose of gain media. So we combined the concept of quantum wells with topological nanostructures to again make the device active. And what we observed was lasing. First of all, when we pumped it below threshold, we observed photoluminescence, and increasing the threshold provided us with lasing. This we observed very narrow line width, which was like around 2.8 nanometers, and uh, a regular threshold behavior. This lasing is from topological valley Hall states, which reside in the corners of this triangle, and like these. We also observed coherence of the lasing emission from these nanos from our topological nanostructure, and we separated these two corners individually, and we observed fringe patterns in the back focal plane, and this proves that our lasing from this nanostructure is coherent. And when we isolate a single spot, we observe that the emission pattern is non-trivial. It hosts a singularity in between, which is a signature of valley Hall states, emission from valley Hall state. Now I move on to the second part of my research. It's the combination of active media with high quality nanostructures. These are the people who contributed. So we come in this part of research as well, we combined quantum wells with Anapole metasurfaces. What are Anapoles? Basically a superposition of electric dipole and toroidal dipole modes, and this leads to Anapole mode. The property here is that in the far field, we don't see any radiation. We have vanishing fields in the far field, which makes Anapole mode a highly confined mode, which means it should have naturally high quality factor. But for single disk systems, there is also higher order multipole scattering, which limits the quality factor overall, which is pretty low. Like a quality factor in single digit is very low, and it cannot be used for a nanophotonic device, especially a laser. So what was done in 2017 was that an array of such silicon disks was simulated, and it was observed that the quality factor increased by 14 times due to near field coupling between unit cells, but still this quality factor of 86 was not enough. As you can see, the resonances are not sharp enough. So it was found that Q factor monotonically increases with like if you decrease the coupling strength between electric dipole and toroidal dipole modes. And this split disks have a split disk kind of structure has a gap in between, which can manipulate this coupling strength. And this array of split disks was then simulated, and it was found that with the tuning of this gap, you could reach Q factors of 10 to the power 6 for, in this case, for gap of 110 nanometers. And this result was reproduced for indium phosphide disk arrays. Indium phosphide disk arrays because, again, they are suitable for quantum well, for using in our quantum well lattice. And again, we calculate this indium phosphide structure, split disk array was calculated and its modes were calculated. And then our collaborators in Korea fabricated this structure again with the same idea as in the 2D topological laser, and we pumped it with the same 980 nanometer laser, and we observed lasing, as you can see here. And the parameters of this structure, the disk diameter, the gap, and the pitch, they were tuned, and it was found that like and we studied the best sample out of all the lasing samples, and we observed and these are the results from the best lasing sample. And we observe very low threshold, and the threshold behavior shows a peculiarity, which is like uh, which which indicates presence of two competing modes, and like a very narrow line width, which was 2.2 nanometers, and these two spatially competing modes were separated. And that we also observed the directionality diagram, and again, like in the previous case, we observed fringe pattern, which proves the coherence of our radiation. These two competing spatial modes were studied by like Professor Mie-resonant, who is also in the who gave us these two images, and like he proved through his calculations that like the indeed one of the modes that we observe here is Anapole mode, and possibly one of the competing modes is symmetry protected BIC, but still investigation is going on to further state anything about it. Now we also now for the final part of this of my research, we also made tunable nanostructures based on phase change media, and these are the people involved. Now, for what is phase change media? It is simple that from one structure, from the point of view of solid state physics, from a change from one crystalline structure to another crystalline structure. For example, in the GIF here, you can see that this is monoclinic structure, and it slowly is changing into a rutile structure. I'll let it play for a while. Yeah. So now it is becoming a rutile structure. This is what happens in vanadium dioxide. At low temperatures, it is monoclinic, and at high temperatures, it is rutile. And at in monoclinic phase, it is insulating, and in rutile phase, it behaves like a conductor, which makes it very useful from the point of view that there is no defect or void creation, because the phase transition is crystalline to crystalline, and hence very useful for like if you have a thin film of vanadium and you want to have this phase transition again and again, it makes it very durable over a huge number of cycles. Now, this vanadium dioxide has is being actively researched by many companies and leading universities like EPFL for creating programmable electronic devices. And it has been shown that vanadium dioxide can be modulated by like electronic methods, mechanical methods, and optical methods. This is a phase transition, and like just for fun, you can see that this is a micromuscle modulate, which is based on phase transition of VO2. Due to this change of stress, it behaves like a, a motor. And this inspired us to look into the aspect of what this phase transition brings to us from the point of view of nanophotonics. It was observed that the transmission, there is high contrast in transmission in near infrared region in conducting VO2 and insulating VO2. And this is what we wanted to exploit. And so we came up with this idea that we came up with this idea that silicon and a high-gens metasurface based on VO2 could be tuned using this by exploiting this phase transition. Amplitude tuning and spectral tuning was what we predicted, and this is what we also demonstrated. So this is a very simple structure, an array of disks of lattice constant around 800 nanometers, and these were fabricated in France by our collaborators. And this was designed as a Mie-resonant high-gens metasurface. And these are our results. The experiment was performed in France, and we did the theory here. And theoretically, we predicted that for 510 nanometers, we could modulate the transmission, like the extinction. So this modulation was pretty high, and experimentally it was not as high, but still this modulation was pretty sharp, which could be very useful for making a kind of switch. And we also demonstrated that for a different disk diameter, that this resonance could be tuned by 30 nanometers, and this 30 nanometer shift can again also be used for some kind of device which could do sensing, or I mean we didn't think much about application, but still, like, this result was pretty promising for using as a programmable optical device. Now we our results were the underpinning concept here was that the fields there was different distribution of energy in multiple modes. Like here you had that electric dipole and magnetic dipole modes are aligned, but in conducting phase you had suppression of magnetic dipole mode, and in this case you have even more suppression of magnetic dipole mode, which led to these kind of results. And in conclusion, I would say that rarer doped nanoparticles and combined with topology gave us robust luminous device which could lock polarization of random distribution of emitters. Like quantum wells along with combined with 2D topology gave us robust lasers resistant to even 30% of disorder in cavity size. Like quantum wells with Anapole metasurface gave us low threshold and low line width lasers at room temperatures. And again, phase change media plus Mie-resonant metasurface, like gave us a tunable metasurface over 30 nanometers and high depth of modulation. Now, for future perovskites plus nanophotonics is what I want to look at. Like spin-coated perovskite metasurfaces would probably laze. And like I also came across a paper which demonstrated perovskite multiple quantum wells, and probably this kind of structure could also be used instead of the quantum wells that we used in our lasing papers, and we could get perovskite based quantum well lasers. Thank you. Any questions?
Adi, thank you very much for a very nice talk. So the seminar is open for questions from the audience. Maxim, please.
Yeah, thank you, Aditya. A lot of interesting results. I have basically a question about this Anapole metasurface, where you discuss the coupling strength between the dipole and toroidal dipole. It would be good if you explain in which sense this coupling is understood, maybe some equations. Is it coupled mode theory, or how you treat this? How you decide to introduce the gap?
Okay. Actually, this coupling strength was not my work, but like I'll try to explain it. So what happens is that when this silicon disk is just a single unit, tuning for tuning, you don't have a lot of parameters. Like if you change the disk diameter, you change both the electric dipole mode and toroidal dipole mode, both of them simultaneously, and like both of them together, and hence you cannot independently tune one of them. You get my point?
Yeah, but what if you drill the holes, because you can keep the symmetry of the disks by introducing splitting, you like reduce the symmetry. That's the thing.
Yeah, I mean, if I'm not sure about introducing holes, but introduction of gap gave us another parameter to play with, and hence you could independently tune electric dipole and toroidal dipole mode.
Okay, more or less clear.
Thanks, Maxim. We have another couple of questions from Sergey Makarov. Sergey, can you ask them?
Yes, can you hear me?
Yes.
Yeah.
Yeah. First of all, yeah, thanks a lot for a very nice talk. A lot of inspiring results. I just have one technical question. So, regarding your results on laser output of your metasurface below, yeah, maybe with where you have where you measure fluence of output.
This
yes.
one?
Yeah, here I just wonder how you define emission fluence of your metasurface, because fluence is quite a size-dependent parameter, and it very depends on the place where you measure your signal. So if you focus your beam, you will have higher fluence. If you defocus, you will lower fluence. So what was the reason, and how you, to introduce a fluence, and how did you define it?
Okay, so how we first of all, why we introduced fluence? We first wanted to do intensity, like intensity versus intensity, but the problem there was that intensity versus we were not sure about what kind of pulse we were getting at the output from the laser, like from the metasurface. Like if you pump it with, like we did not measure the pulse itself, and it was not a perfect Gaussian pulse, so we did not want to go into that, but still we wanted to keep the units on both the axes to be same. So we wanted to remove this time factor. So we came up with the idea of pump fluence. Now how we measured it? How we measured it was because we had an infrared camera, and we knew quantum efficiency of our infrared camera, and we kind of reverse engineered it at like okay, so this is the let's say this is our image, like this is the camera output, and we measure the number of pixels, and like we integrate the number of counts from, like we add up or the total number of counts, we divide it by the area of the the total area which was radiating. This would give us this dimension of centimeter square inverse, and you reverse calculate it with the quantum efficiency of the camera, and then you can get number of photons, and you know the wavelength of emission spectrum, so you can calculate the energy of each individual photon, and then that's what gave us this unit of emission fluence. Did I answer it?
Yeah, in principle, yeah, understood. Maybe average output of power would be also interesting parameter, because it's which you can just measure by power meter simply. So maybe this is also can be interesting for some from technological point of view. So if you allow, may I ask a second question on a similar slide or
Yes.
concept of so I just wonder regarding Anapole lasing. So once this is not really one true mode, this is like superposition, yeah, of two modes in a far field, but in case of inversion of population, so I believe one of these modes just takes all inversion of population, and in this case, in lasing mode, we can expect domination of one of these modes, or dipole or toroidal dipole mode. In this case, do you believe that you really deal with this high Q state, Anapole state, or we start to deal with one of these modes, and maybe we have something different from Anapole, true Anapole mode?
Again, from experimental results, we don't have a good way to verify this, whether we are actually having lasing from Anapole mode or not. We, like, for this purpose, we are relying on theoretical calculations which are still underway. Like, we don't have a very concrete answer to that, to be honest, but like still like, we believe that the Anapole mode is the closest to the observed wavelength of lasing. So probably Anapole mode dominates, but like, again, not sure, because calculations are still underway.
Yeah, thanks. And just final remark that you mentioned the perovskite quantum well. So in principle, yeah, we are quite open to collaborate, because we have two-dimensional layered perovskites in our lab, and yeah, they demonstrate good properties. So maybe we can.
Yeah, like actually, what I would think is that at least we could make something like a membrane, membrane-like structure, and like at least implement these kind of designs. However, perovskites offer us to work in visible wavelength, and we can probably design another nanostructure. I haven't worked on it yet, honestly, but I really do want to. I'm really more than happy to. And I'm also working these days on active nanophotonic simulations, in which we combine rate equations of active media with FTTD simulations. I'm still learning them, but like, probably once I'm ready, I would be able to simulate some structures with perovskites deposited or with perovskites on them, and then we can probably predict if we are getting something interesting. And then, thank you.
Okay. So while we are waiting for other questions from the audience, I would like to ask a couple of them. So the first one is regarding the first part when you use this topological zigzag chain.
Yeah.
And so I'm wondering, so you say that one of the motivations of the system is the control of the emission polarization of your active medium. So I'm just wondering, why can't you take your active medium with its emission line and take a single nanoparticle of anisotropic shape? So along one dimension, you will have the resonance which will fit the emission line, and the other one will be out of that. It could be either plasmonic or dielectric, and would also provide a polarization of the emission. So what's the advantage of the topological structure here?
Well, in our case, to be honest, I haven't tried it yet, like with single nanoparticles, but in this case, for topological nanostructure, you also get 5 times enhancement in emission, and again, these like there is like we did not compare it as such with single nanoparticle case. Like
I'm just wondering whether it could be an anisotropic Huygens-like nano antenna, which will provide the Huygens regime along one dimension at the frequency of your interest.
Definitely.
And that will give you the selectivity in polarization and quite a nice enhancement.
Definitely. For if you use a single nanoparticle, like let's say ellipsoidal nanoparticle, you can also have a similar effect. But I'm not sure, like whether you can achieve enhancement of the same level or not, or whether you can like how effectively it can control polarization. Like I don't have a quantitative comparison yet.
Okay, I see.
But for sure it should work.
Okay. So just maybe a comment I will drop to a chat. So our colleagues from our department are also working with phase change materials, and that's also a paper in Optical journal where they're studying the switching, non-volatile switching of a metasurface, all dielectric metasurface with germanium strontium telluride. Just to know this, please. Keep it in mind. So guys, I see we don't have any questions more. We're a little bit than 1 hour long. So Adi, thank you very much for this talk. And I would like to thank both speakers and the audience for the discussion. So I believe that it's a nice tradition for our seminar to host not only professors and postdocs, but also PhD students from other groups. And for this reason, next week, we have another PhD student. So the talk will be given by Mrs. Anna Fedotova from the group of Professor Isabel Staude from Friedrich Schiller University, Jena, and she will be talking about nonlinear photonics with lithium niobate. So, and in order to stay updated, just subscribe to our mailing list and go to our YouTube page where we can find all the seminars, most of the seminars we have here. And thanks again to everyone for joining the seminar. Stay safe and good luck.